In order to start understanding chemistry, we got to start at the very, very, very beginning of the science. So when you use the word chemistry, one will think of the word reaction, someone will think of the word atom. So what I want to do before we really jump in and start talking about, the actual science itself, let's talk about the historical context of the atom. Where does this word actually come from? And so the first place that the word atom is actually being used was about 450 BC. Okay. And there was a Greek philosopher, and his name was Democritus. Okay. And he was Greek philosopher. And what he did was he actually coined the word atomos, which is the Greek word for atom. And he defined atomos as very small particles that are indivisible. Now, at this point in the story, there were only four known elements in the world: earth, wind or air, water, and fire. Okay? And Democritus's view was that if you pick up some sand and roll that sand between your fingers to the point where you grind that sand down to become dust, and then you grind that dust to the point where you can't grind it any further, that's what an atom is. Okay? Now, Democritus's views that this is an indivisible small particle. This is the smallest particle you could ever have. Democritus's views were actually challenged by Aristotle and also Plato to an extent. But this idea that there is this small particle that makes up everything in the universe, that idea, which we call atomism, actually survives. So let me get this down. So Democritus's views were challenged by Aristotle and Plato to an extent, but the idea of atomism survived. Okay. All right. And this idea, I mean, think of it this way. This is 450 BC. And Democritus was a student of Socrates. Okay? So this is like really ancient Greece. And if you think about all the known information, all the known knowledge of that world, it survived the ancient Greek Empire. It survived the burning of the library in Alexandria. The Roman Empire came and went. You had the rise of the Holy Roman Empire, then the rise of the French Empire, the English Empire. So we're talking about 2,400 years, 2,450 years that this idea has been around. Okay. And up until, while this view was being challenged, this idea kind of persisted. And it really wasn't until the very first experiments that were done in chemistry. So, early experiments in chemistry. And this was about the time of the 1660s. So, we're at the time of the scientific revolution. Okay. The earliest experiments in chemistry actually supported Democritus's views. Okay. And these experiments also provided working definitions of the word element and compound. And those working definitions pretty much remain today. There's been slight modifications, but those working definitions are still in use today. And at the time of the scientific revolution, we get to the age of enlightenment, and we have many, many different experiments going on at a time. And as this scientific inquiry and this scientific exploration really takes hold, it actually leads to a watershed moment in the history of chemistry, where the English school teacher John Dalton actually tries to formulate an overarching idea for our science, chemistry. And so this is called Dalton's atomic theory. Dalton's atomic theory has 4 postulates, or 4 main ideas. And so what I'm going to do is let's break down these main ideas one by one. So the first main idea is this: elements are composed of extremely small particles called atoms. So this first postulate is actually a throwback to Democritus and his idea back in 450 BC that everything is made up of atoms. Now here's the second part. All atoms of an element are identical. They're going to have the same size, the same mass, and the same chemical properties. Atoms of different elements will be different from each other. Okay. So that second postulate says this: all atoms of an element are identical. They have the same size, the same mass, and the same chemical properties. Atoms of different elements will be different from each other. Okay. Let's talk about the third one. The third one says this. It's gonna deal more specifically with compounds. Compounds are composed of atoms of more than one element. When compounds form, they form in small whole number ratios. They form in, simple whole number ratios. So that means if you've got hydrogen, you've got 2 of those hydrogens, you could combine it with one oxygen, and that's a compound. Or you could combine the 2 hydrogens with 2 oxygens, and that's also going to be another compound. So atoms are going to come together, and they come together in these simple whole number ratios to form these compounds. Okay. All right, and then finally, the last postulate. Last postulate says this: a reaction involves the separation, combination, or rearrangement of atoms. You cannot create nor destroy atoms in a chemical reaction. So that means if you start with oxygen on the left-hand side, you start with oxygen, you better have oxygen somewhere in that on the finished side as one of your products. Okay. All right. Now, for the most part, in 1808, when John Dalton's theory was first brought out, this hasn't really changed a whole lot. Now, there have been a couple updates. Like, for instance, when we talk about postulate number 2, all atoms of an element are identical. They have the same size, mass, and chemical properties, and that atoms of different elements will be different from each other. We know that that's not exactly true anymore, because you can have elements, you can have atoms that are the same, they have the same size, they have the same chemical properties, but they have different masses. So we know that the existence of isotopes, where you have the same number of protons but different number of neutrons, you can still have atoms of the same identity, has the same chemical properties, but they're going to have different masses. Okay. And then also at the bottom, postulate number 4 says this: a reaction involves the separation, combination, or rearrangement of atoms. You cannot create nor destroy atoms in a chemical reaction. In a conventional chemical reaction, absolutely true. However, with the advent of nuclear chemistry, we know that that's not exactly true anymore, that you can take one atom and convert it to another atom if you use a proton, a neutron, an electron, positron, alpha particle, whatever you're going to throw at that atom. It's possible that you could start with one atom or one element, and you get something completely different. Now, Dalton's atomic theory also helped to explain some of the other laws that have been out since the days of Newton and Boyle. And so one of the first laws that John Dalton's postulate actually helps explain is the law of definite proportions. And this was thought of by the chemist Joseph Proust in the year 1799. And he said this, Proust wrote this: the different samples of the same compound always contains the same elements in the same proportion by mass. So if I take a sample of water, in one sample I see that the compound is H2O. If I take another sample of water, it most likely, the molecular formula likely will also be H2O. So if you're always making carbon dioxide, you always have to have one carbon to 2 oxygens. Okay. Now, this sometimes gets confused with the other law that says the law of multiple proportions. And here's what the law of multiple proportions say. If you have 2 or more elements and they combine to form more than one compound, the masses of one element that combines with a fixed mass of the other element are in simple whole number ratios. small whole number ratios. So if you're going to have a compound that has, like, let's say you're going to take a sodium and you're going to connect that to a chlorine, they are going to come together in form small whole number ratios to make a compound. So you need one sodium and one chlorine to make sodium chloride. Okay, or likewise, if you have two hydrogens and one oxygen, they can combine to form water. All right. Now the final law we're going to talk about is this: the law of conservation of mass. The law of conservation of mass says this: that matter cannot be created nor destroyed in a chemical reaction. Now, this one is actually pretty important when we get a little bit further along in the course. In Chapter 6, when we start talking about thermodynamics, this idea is actually going to be really important to us. And this is the start of that idea, that matter cannot be created nor destroyed during a chemical reaction.